Assalamualaikum. Today we will present about solar water heating system, and I will to introduce my team members. First is me, FATIN DARWISYAH binti SAMSUDIN. Second is Nik SABRINA WAFA binti Nikmi, and Nur ALIA binti ISMAIL, and the last one is Nur Umairah binti Ishak.
This video presents a simulation of a flat plate solar water heating system using SolidWorks flow simulation. The system was designed to resemble a small-scale solar collector. It consists of several key components. From the bottom, as you can see, it is an casing, insulation, absorber plate with fins, and glass cover. The simulation included various solid material with realistic thermal properties, glass wood insulation with very low thermal conductivity to prevent heat loss, aluminium casing for lightweight structural support, glass glazing for trapping heat while allowing radiation in, copper for the absorber plate due to its high thermal conductivity. Each material was assigned correctly to reflect real-world behavior in the heat transfer model. Next, boundary conditions were applied to simulate operating conditions. Water enters the system at 10 meters per second with an initial temperature of 30 degrees Celsius. The environmental pressure on the glazing surface was set to atmospheric pressure. Gravity was enabled to account for natural convection effect. The top surface of the copper plate was exposed to simulate solar energy. Next, global goals were set to monitor the system thermal performance. This included maximum and minimum fluid and solid temperatures, wall temperature, convective heat transfer rate, mass flow rate, and the average heat transfer coefficient across the interface. The mesh was generated with approximately 63,000 elements and 141,000 nodes. This level of resolution ensures accurate capture of temperature and velocity gradients, especially at the copper-water interface. This cut flow shows the temperature distribution in the water as it flows through the collector. The fluid heats up from 30 degrees Celsius to approximately 47 degrees Celsius as it passes beneath the copper plate. Flow trajectories confirm smooth water movement and good interaction with the heated plate. The result will be compared with the theoretical calculation involving conduction, convection, and radiation to evaluate overall efficiency. This simulation provides a valuable insight into thermal behavior of the solar water heater under real-world conditions.
For this part, we did the theoretical calculation to estimate heat loss from the collector panel through conduction and convection. For conduction, we used the material properties of aluminium with a surface area of 4.83 meters square, a thickness of 0.157 meter, and a temperature different from 47 Celsius to 34.8 Celsius. The result was 76.96 kilowatt of heat loss by conduction. But for convection, we use the same surface area and a convection coefficient of 20.968 with an air temperature of 25 Celsius. The heat loss by convection was 2.23 kilowatts. Based on this theoretical calculation, we can see that the heat loss by conduction is much greater than by convection. This makes sense because aluminium is a highly conductive material, so the most of the heat will move through it instead of escape through the surface into the air.
Okay, next is this for discussion and analysis. From the analysis, we get this simulation has confirmed that the system works as expected with stable result. Key thermal parameters are clearly identified, and critical areas of heat conservation can be highlighted, providing insight for potential design improvements of the solar water heating system.
Assalamualaikum, my name is SABRINA WAFA. So today I am going to conclude our project. So in conclusion, the simulation result clearly show that the solar collector performed as expected. The fluid temperature increased steadily under sunlight, proving that the system can effectively absorb and retain solar heat. The use of copper absorber plate and glass glazing worked well to capture and transfer heat efficiently. Overall, this design achieved its goal of providing a simple, efficient and sustainable solar thermal solution. However, there are areas where the system can be improved. For example, better insulation could help reduce the heat loss, especially during cooler weather or at night. We also recommend exploring alternative materials that are more cost-effective or offer better thermal performance. This project has shown that with the right design and material, a solar collector can be both practically environmentally friendly. It provides a solid foundation for future enhancement and real-world application.